Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the MSR Faculty Summit, and this is the session on interaction for machine learning. There are too many pieces here, so I'm getting confused. So let me see how to make this work. Here it is. Okay. All right. So this is a panel on interaction for machine learning, and that's co-organized together with Dan Bohus, H.A. Kamar, Li Hong Li, Jason Williams, and myself. And before we get into the panel, I just wanted to give you a brief overview of what we hope this panel would be about. And essentially, as the title suggests, right, it's interaction, machine learning, looking at human and a machine learning system together in an ecosystem. And there are at least a couple of ways we can think about doing so. So the first one is, a human helping machine learning system. And there are many examples that we've seen in the literature. For instance, humans can help a machine learning algorithm by providing some labels, some kind of preferences, some kind of guidances, choosing right kind of model, choosing right kind of data sets, features, et cetera, right? And of course, traditionally in machine learning, usually a lot of discussion is around the algorithmic aspects, but here we are emphasizing the ecosystem. And the second aspect is machine helping the human, right? So amplifying human capabilities, for instance, like web search, right? Of course, looking through, millions and millions of documents is infeasible, but if you have some kind of machine learning, some kind of web search, you can greatly improve what a human could learn by looking and browsing through those documents intelligently. So interestingly, we are looking towards an engagement between a human and a machine in a manner that's an interactive give and take, leading to greater results, right? And specifically for this section, we would be focusing on the first aspect, which is human helping the machine learning. And I'm going to explain what do I mean by that. So, last night when I was preparing my deck at the last moment, I started thinking about, can I come up with a single sentence that would describe, what this panel is going to be about. And this is best I could come up with, right, which is how to modify a behavior of a machine learning system by interacting with it, right? It's a very general statement, but I think it summarizes some of the intuitions and some of the goals that we aim to achieve in this line of research. So to give you an example, let's look at a scenario of, say, a spam filter. You guys get spam, I'm sure, like all of us in the world, and you have some kind of a filtering system. It can be a machine learning system, and the goal of this system is to, figure out spam from not spam. Very simplistic, right? Whenever the spam filter makes a mistake, what do we do, right? Traditionally, machine learning researchers would say, feed it more labeled data, right? And it might change the behavior of the system. But I think we can go beyond this label elicitation. So to give you an analogy in real one, so instead of a machine learning system, if you had a personal assistant, right, and whose job was to sort some of this mail for you, right? And if they made a mistake, probably you're not going to go and feed them more data to learn from it. You're going to probably have a conversation with them. You're going to explain to them why something they did was not correct and hope that that would modify the behavior of your agent, right? So there is a disconnect between how we interact at a human-human level with how we interact with the human and machine level. And we are hoping that we can come together and have a discussion on how to sort of minimize these kinds of gaps. All right, so, again, just to summarize, here is a pipeline, This is a machine learning pipeline, very standard. You start with some algorithms. You have some data label collection phase. There's feature extraction. You fit a model. And then, you have the results, right? Again, most of the time, we are thinking about, human involvement here, where they are labelers, right? 99% of the times when I go to a machine learning conference or a other computer science conference, I tell them I work on interactive machine learning. The first question I get, oh, is it active learning? And I want to start to think about problems where we can do interaction just beyond data elicitation, right? Of course, a natural way of incorporating a human involvement is at evaluation, where because a lot of basically use of these machine learning system is when an end user is using it, right? And if they don't like it, they'll give you a feedback. But it seems that there are many other places where we can start thinking about this kind of interaction, right? And this is, we are hoping this panel will be about. And again, instead of human as a labeler, we should start thinking of human as a designer. Already, a human is in the loop in designing machine learning system. They are the one who chooses the algorithms. They are the one who chooses the features. They are the one who chooses, what optimization strategy to work on. So why just think of a human as a labeler, but go beyond it? Think of it as a designer, an explorer, and even a computational processor who can give you some features that you might not be able to compute automatically, right? And cutting across all the space as different machine learning methods that we can think of, right? So with that, let's dive into the panel straight. We have a very, elite group of speakers today. So we have James Fogarty from University of Washington. So James, if you just want to, they're all sitting up front here. So that's James. And then we have Lisa Gatour from University of Maryland. Patrice Simard from Microsoft Research. So Patrice there. And Jerry Zhu from University of Wisconsin-Madison. So they'll each be speaking about about their thoughts on this general research directions. So the way we are going to do is that we'll have some short talks by speakers, right? And it'll be in the following order. Again, the goal of this whole session is to be more discussion-oriented. So please do ask questions. So I see there are a lot of respondents and a lot of participants. So I think it'll be great if you could engage in some interesting dialogues. And once after each talk, we'll spend some time on question and answers with each individual speakers, and followed by a deeper, bigger level discussion at the end of the talks, right? So with that, let's dive into before that, I also want to mention that following this panel, there is another panel on the mirror, mirror opposite of this problem, which is machine learning for the interactive system. So where the idea is that the goal is interaction, and then you are thinking about how machine learning could help. So I hope a lot of you will attend that session as well, and that's in this room following the session, right? So with that, let me welcome our first speaker. So our first speaker is Jerry Zhu from University of Wisconsin-Madison. And I have followed Jerry's work for quite some time now, and he's done some very interesting work in how humans learn and how we can learn from these behaviors and incorporate that into machine learning system. So with that, I give the podium to Jerry. Let me see. This is PC6? Okay. Make sure he gets the.
Ooh, that's interesting. Okay, good. So can you hear me? Yes, okay. In the spirit of encourage discussion, I think we should call this 3 discussion topics. So I'm going to discuss 3 points that I think can characterize a hybrid human machine learning system. The first one, let me just cut to the chase. The first one is we can actually model human being not as some gray box, black box, but with precise mathematics that's done to a machine learning system. Okay, and this such math is the same for machine learning and for human learning or cognitive science. So I'm going to start with a game here. I give you 5 English words there, and I also labeled them. These are binary labels, either A or B. Okay, so each word has a binary label. Can we please guess what rule I used? Anything is fine.
Green versus not green.
Green versus not green. Excellent. Excellent. human-related versus not human-related?
There is letter A, and its font is A.
There is letter A in A, and not letter A in B. 7 letters. Yeah. You are doing great. You are overfitting. And that's because these are random labels. But that's an amazing fact. I give you random labels, and if you have the ability to come up with hypotheses that would fit a training set with random labels, that means your hypothesis family is rich. That's your mind is very rich. And that's something we want to quantify in machine learning. This is exactly the concept of VC dimension, okay? Except that in this case, we're measuring it with a variant called Rademacher complexity. And that's something we can actually compute doing human experiments to try to work out what this is. Now, forget about the scary math. That's not important. But what's important is it's very intuitive or counterintuitive, whichever way you look at it. If we have a piece of model family, in this case our mind, that's rich, that has high complexity, then we actually have higher tendency to overfit. And this richness depends on many factors, such as whether the stimuli you see are shapes or English words. The curves here, they basically show that the higher is more complex. So we actually have more capacity in overfitting random words. Okay? Now, this is important because whenever you train a classifier, you give it a training set. How do we know that the classifier actually learns the underlying thing behind those training sets are not overfitting? We don't. So theory can quantify how much overfitting is likely, and that's precisely what this kind of mathematics can reveal, even for human learning. As a second example, we can model humans, in particular their classification behavior, with machine learning theory and machine learning models. This is an example of semi-supervised learning, and many of you are familiar with the concept, but here is an example. So look at the left plot. The x-axis is the stimuli space. Think of it as, let's say the angle of a line. So something like that. And there is a particular threshold where line of this form is A, class A, line of this form is class B, and so on. You give people training data in the form of at -1, this angle, you say that's a negative example. At angle 1, that's a positive example. Okay? After that supervision, humans will come up with a concept in their mind, and they will put the decision boundary in the middle of your training examples. That's to be expected. That's supervised learning, and that's how psychologists model humans. But what's interesting is if then you test them, okay, you test them on a bunch of test data, lines of different angles. Now, these are test data, so they don't see the correct answer. They only see the test examples they predicted. However, if you give them examples that's drawn from, say, this blue distribution, which has 2 humps and the trough, what will happen is after testing, the decision boundary in their mind would actually shift to the trough. So they cannot retain what they were taught in the beginning. They will be influenced by test data, and subtly. The same thing like in active learning, we can model human behavior. If you allow a human learner to do active learning, to select queries, as opposed to just give them random training data, it turns out machine learning theory can also quite well model their behavior. I'm not going to go into the details of this. So these examples really illustrates my first point, which is we should treat human being as just another computational system whose mathematics we can hope to understand. Okay. Now, let's move on to the second point. The second point is we're talking about interaction in a very special way. We're actually looking at a form of helping, one party helping other, or in other words, teaching. Now, if you have a human and you have a computer, human teaching machine is the topic of this workshop, but you can also look at the other way around, where a machine would select good examples to teach human, and that would be a topic for education. In either case, however, we are looking at something that's not quite machine learning, or not what traditional machine learning has been studying. Okay, I want to make that point, and the point is there is actually a theoretical way to define what teaching is and what is optimum. So I will illustrate that by the following example. I'm going to, again, use this line that's the one-dimensional feature space. So imagine you have a one-dimensional binary classification problem where there is, the vertical bar is where there is this true, ground truth threshold. To the left of it, you have negative class. To the right, you have positive class. Okay? So that's the true target you are supposed to teach, say, let's say teach a computer. Okay? Now, how do you teach? The simplest case is you as a teacher generate random, let's say, uniform IID training example. So you sample a bunch of points uniformly along the line, and you label them according to on which side of the threshold they fall into. Okay? So in this first example, passive learning, we have 8 points. Okay? Now I ask you the following question, right? If you have a machine learner, you receive this training set, and you know the true concept is a threshold function, then it's clear that you should put a decision boundary in between the closest positive and negative example. Okay? The question is, if you do that, let's say you put it in the middle of that, how far is it from the true decision boundary? Okay? That's a random quantity. It depends on the random training example you get. But roughly speaking, with large probability, the error you make is 1 over n, where n is the training examples. And that is because with n training examples, you roughly divide the space into n pieces. So the space between them is on the order of 1 over n. Okay? So that's okay. It decreases as n increases, as you have more training data, but not great. Now, if you're familiar with active learning, that's where the learner the machine learner would actually propose a point and say, hey, please label that point for me. And your job is a labeler, right? In this case, in a noiseless case for 1D threshold function, the best strategy is actually binary search. You are supposed to, the machine is supposed to ask the first query at the middle of the range and say, what is this? And then move on and divide up the remaining range depending on the true answer. Okay? If you do this, as you can see, the error decreases much faster. Okay? It's exponential decrease, so we're doing much better. Okay? But what I want to say is, if you actually think about teaching, okay, that's not active learning. If there is a good teacher who knows the concept and who can design the training set, he is supposed just to design, 2 training examples, right next to the decision boundary, and give that training set to the machine learner, and we're done. Okay? And you can make the error arbitrarily small by making those 2 points close to each other. Okay? And this is captured by the nice work of Teaching Dimension, which says that for this kind of concept class, you only need 2 examples to teach. Okay? There are many interesting alternatives, such as you want to, for a realistic system, especially for human learners, you may want to not just give 2 examples like this, but maybe you want to start from very easy examples. That means distinct. That means on the end extreme of your feature space, and then gradually give examples moving toward the decision boundary, and so on. Okay, so the interesting thing is, I believe there are mathematical ways to quantify this, to turn this into an optimization problem, such that we can design optimum teaching sets. Okay. The last thing I want to say is, we know that humans are not rational, okay, all the time. So maybe they will not, when they interact with a machine, they may not be that optimum teacher. But for machine learning people, we also shouldn't think of the human being that's interacting with us as just a data provider in a sense like an IID data provider. Okay? The human is actually trying to do something that's sensible that will help us. And our machine learning algorithm should anticipate that. So what do I mean by this? Let's look at an example. Let's say I want to train a text classifier which distinguishes several sports topics. Okay? So my topics in this case happens to be 5 kinds of sports. How do you do that? Basketball, hockey, and so on. Okay. One way to do this is to say, well, let's have a human annotator, but this human annotator can do the following. Without any documents, without anything, he's just going to sit there and think for a while and give us keywords that he thinks is indicative of each topic. Okay? So in this example, for example, let's look at the left column. The human might just type in basketball, hoop, dribble, etc., and say these words belong to basketball, or whenever you see these, that is a potential for the basketball class. Now, this is labeling features rather than labeling documents. But it's also interesting how these labels are generated. We didn't ask them. The machine didn't ask them didn't provide a list of candidate words for them to label. These are purely thought about by the human being. Okay? If this is the case, what can you do? Well, there's some indication that the first words are more important in some sense, okay, because people thought about them immediately. How do you capture that? And in fact, some of the words would repeat, you may think of this as a model where each class in humans' mind is a multinomial model. Okay? Each keyword has some probability, and maybe that human teacher is drawing from his multinomial distribution. Okay? And here's a plausible model to do things like this. This is an urn ball model, so each urn is a particular class. In this case, maybe basketball. Each ball in there is a word, okay? And the size represents the unknown importance. And this is a generative model for how humans would generate the list. He can draw from that urn. So maybe the first draw is this green thing, okay, which may be the word basketball. And we're going to do the following. We're going to create a scenario where we're doing sampling with replacement, except that when we put this ball back, we reduce its size. Okay? So we will have an urn like that after the first draw. And then we repeat this process. This would be an interesting model to fit the kind of list that humans generate. And just to show you that it actually improves accuracy, I'm showing you a bunch of numbers. Basically, the bigger, the better. And this first column is when you use this model. OK, I'm going to wrap up. Here are some references. But I want to make 3 points. To wrap up, I believe humans can be modeled precisely. And teaching can also be quantified precisely. And when humans interact with machines, even though they're not optimal, we still want to take advantage of the specialty that they are human beings. And there is something that hopefully we can capture with our model. OK, thank you.
All right, so if there are any comments, questions for Jerry from the audience? Yeah. Do you want to give the mics to Jensen, please?
Thanks for a nice talk. So when you talk about modeling humans, the models could be also task dependent. And my experience shows that humans also learn with the data. So there's a kind of joint modeling of the human being's understanding and the data.
Yes.
So would you like to comment on that?
Yes, that's a very good point. Usually when we think about human as a labeler role, we view human as the oracle, as we call it, right? And human is definitely not a simple oracle. They learn, that's one thing, but in many cases, they sort of adapt. They notice what the system is asking, and they try to sort of manipulate their own answers to fit the system or to try to improve the system. So that definitely needs to be modeled as well.
Great. So one of the things I noticed is that the first experiments you did, human beings were generating features. That's the perspective that I had, instead of them generating classifiers, right? So I'm just wondering, instead of thinking about Rademacher complexity, maybe think of human as a feature generator. That's probably a more appropriate modeling. Just
right. So so that's definitely true. I mean, the Rademacher case is actually when a human is a learner, more to describe that.
Yeah.
But yes, humans can generate. I mean, the last example where they propose words. That's like they give you features, although the features are still simple, they're just words. You can imagine they give you more complicated things, such as, for example, engrams. But I think you have in mind more complicated things like rules.
Yeah. Great. Yeah, Dan?
Hey, Jerry, thanks a lot. So I was wondering about the experiments that show that humans learn on test data without the labels afterwards. Can you say a bit more about that? How well do we understand how humans do that? And how does that compare with what machine learning techniques today can do today, like semi-supervised learning and so on? Like, are they structurally very different? Do we have tricks that we haven't yet computationalized?
Right. So this is now well understood in the case of simple categorization tasks in humans, meaning that if you give humans a well-defined classification task, you train them till they saturate, and then you test them. But you test them with like interesting distributions and so on. Their decision boundary almost always get influenced, changed by your test data. That is well modeled by many existing semi-supervised learning models, like the mathematical fit is great. So in that regard, we know the effect is there. Whether that's useful, whether it's a feature or a bug, that depends on your perspective.
So just to follow up on that, so when you say semi-supervised, is it certain kind of assumptions you can learn from it? Like, is it wide margin assumption or a manifold assumption, or is there something we can learn about that?
The research so far has not been able to distinguish the subtle difference between several assumptions, but it looks like people are doing a very strong, if you're familiar with the literature, a cluster assumption. If they notice that there are clusters in data, especially in test data, they hang on to those. So the clustering assumption seems to be a good fit to the behavioral data.
Okay, great. So with that, let's move on. I think we'll have more question answers for the panelists once we've gone through all the talks.
Thank you.
Yep. Thank you, Jerry. So next we have Lisa Getour from University of Maryland, and she's done some exciting work on using interaction for graph-based problems. And let's please welcome Lisa. Let's see.
I think I'm supposed to be piece 5. It's supposed to be P5.
Oh, I see.
How do you?
Okay.
Great. Okay. So I'm going to be talking about interacting with graphs in particular. And part of the reason I want to talk about interacting with graphs is that data is not flat. In particular, big data is not flat. So as machine learning researchers, we really like it when you give us your input matrix that has the columns are the attributes and the rows are the instances, and then we'll apply our methods to them. But when you think about the kind of data that's out there and that is in the wild, most of it is multimodal, multi-relational, spatio-temporal, multimedia. So you have different kinds of entities, you have different kinds of relationships between the entities, you have spatial relationships, temporal relationships, you have text, you have video, all kinds of things. And I'm going to use the shorthand graph data for that. But realize when I talk about graph data, I really am talking about this kind of rich, structured data, but it's just that this is too much of a mouthful to say over and over in the talk. And so I believe that there's a great need for machine learning algorithms which work on graphs. That's my main area of research. There's a lot of other people that are developing machine learning algorithms for graphs. So you can think of joint probabilistic models, you can think of tensor models, multi-relational latent variable models, lots of other things. And for this talk, I'm going to abstract from that. So I'm not going to be talking about the particular methods, graph machine learning methods, but I do want to, before I get into interaction, give you 3 patterns for machine learning algorithms that are applicable to graphs. And these 3 patterns are what I'm going to call collective classification, link prediction, and entity resolution. So in collective classification, the idea is you're trying to infer labels for the nodes in the graph. And you want to do that in a way that makes use of the kind of information, local information that you have available for the node, but you also want to make use of information about the structure of the network, information about the labels of the neighbors, and so on. The second kind of pattern is where I'm trying to infer the existence of a relationship. So an existence of an edge in the graph. And again, I want to use information about the nodes that potentially participate in the relationship, but I also want to do this in a collective way so that, links depend on the existence of other links and so on. So I can't just make this prediction in isolation. And then the third pattern that I want to kind of prime you guys with is entity resolution. So figuring out when you have nodes in the graph, when do they actually refer to the same underlying entity? And this is a form of kind of clustering the nodes in the graph to figure out which ones have the same semantic meaning. And these are kind of the patterns that I want you to think about. They're simple, but they're still a little bit deeper than just vanilla supervised learning or clustering, taking into account this structure. So what about interaction? Here I'm thinking of, we have a user, the user's interacting both with the data, the user's interacting with the machine learning algorithm, the user's potentially also interacting with the system, that the machine learning algorithm is watching the user interact with the system. Or that system is the machine learning algorithm. I'm going to mainly focus on the first 2 and talk about what's different when you're thinking this way about graphs in the graph setting. So I want to kind of talk about 3 nuggets, which are the unit of interaction, the context, and comparison. I'm going to use those patterns to make these a little bit more specific and talk about them from the perspective of graphs. And these concepts, for an HCI researcher, I don't think they're terrifically novel, and I apologize if I'm characterizing them incorrectly. But I think from a machine learning algorithms perspective or researcher perspective, maybe they're not always so much the focus of our thoughts and the motivating us. So the first one is unit of interaction, and this has already been touched on, that in standard, say, active learning setups, you think of acquire a label. So that's the unit of interaction. Maybe it's figure out a preference relationship. Maybe it's a must link, cannot link kind of relationship. And I want to propose one slightly richer interaction that is actually very natural and works well in graph settings. And that's active surveying, where you acquire a node and you also acquire its links at the same time. And I'm going to kind of illustrate that in the context of collective classification, where I'm trying to infer labels for nodes in a graph. So suppose that I have this network, and suppose that my classes are positive, neutral, and negative. So maybe it's towards a product, maybe I'm trying to do viral marketing or some sort of information diffusion kind of thing. So there has been work in active learning in this setting, and most of that work tends to assume that the network structure is observed. So I'm conditioning on knowing the network structure, and then I'm going to go in and figure out who should I survey, who should I acquire a label for, in a way that I'll both improve the accuracy of my classifier, but at the same time I'll improve my predictions on the unlabeled nodes in the network. And going beyond this, we can say, well, oftentimes you don't have the network structure observed, and so you have to reason about only partially observed links in this and take that into account. And so in this setting, a notion of active surveying, where you go in and find an individual and then you acquire their label and also the links to their neighbors. And continuing on in this process, acquire more information. And we've looked at this problem in a couple different settings. Also, actually, Paul Bennett here, together with Jen Neville, have looked at this. These are results for a particular case where we're trying to identify key opinion leaders. And in the setting, I'm not going to go into details about exactly what that inference problem is, so it is kind of a richer inference problem. But the important thing is, by developing an active learning setting that can do this active surveying, we can reduce the number of surveys needed significantly. And when these are things where you're actually going out and physically visiting someone and interviewing them and so on, this is an important savings. So the next kind of nugget that I want to get to is talking about context, and in particular kind of how one shows the context for decision making to a user when one has graphs. So in a graph, we can show just a single node in the graph, for example, and that's probably too little context. We can also show the whole graph. That's probably too much context. And instead, what we should strive for is showing the right relational context to whatever the decision task at hand is. And I'm going to describe a particular relational context that we developed for a tool for doing entity resolution. And so this is dedupe. I'm not going to go into details about the tool itself. If you're interested, you can go to this website and download the code, and there's a longer video on it. The thing that I want to highlight is I want to highlight this visualization, where this visualization shows the relational context. And let me set this up and explain the data a little bit. So in this data, I have nodes which represent authors, and the links between them represent co-authorship relationships. Unfortunately, this data is very messy, and it turns out that a lot of those authors turn out to be the same. And so what we developed is a visualization where the nodes here, the square nodes, those are the things that are the potential duplicates. And then we show the shared neighbors. So these are the people that we already know are the same nodes that are co-authors of both of these potential duplicates. And on the sides, we show their non-shared neighbors. And it turns out that this view allows users to interact with the system and quickly get a sense of the relational context. So this is just a little video showing it for a bunch of different settings. And you'll see that the thing that's nice about this is we have this stable semantics for the visualization. So we always have the two potential duplicate nodes in the same place. We always have their relational context set up in these substrates that have semantics associated with them. And we're able to navigate and in fact, we can even see potential duplicates in their non-shared neighbors if we like. And so this is a case where I think we found a visualization that was well suited towards the decision task at hand. And the last kind of nugget that I want to try and illustrate is in the context of comparison. And this, I think, is really important for machine learning algorithms operating in complex spaces. How do you compare the output of different models? Comparative analysis of machine learning algorithms. And in the case where you have flat data, we can use a confusion matrix. Even that is challenging. There's research here Ashish and others have done in doing this. But now what about if we talk about graph data? So we've developed a tool called GPair, which is for graph comparison. And in this, kind of the nugget, the visualization nugget for this is how we encode a lot of information in a single node that we're going to show on the tool. And the key thing is that we'll show information from model 1 on one half sphere of the node and model 2 on the other half sphere. And we're comparing algorithms that are doing collective classification. So they're outputting distributions over labels of the nodes, and we want to compare these distributions. So the way that we do this is we encode, first off, the color coding of the node is the predicted label according to either algorithm, so the most probable label. And in this example, if we have neutral and positive as the possibilities, we can quickly see if we have a solid node, the two models agree. If we have a two-tone node, that means that they disagree. We can encode the confidence by the fill area. We can encode the, if we want more information about the similarity of the distributions, we can encode the eccentricity of the node so that if it's a round node, we know that they really agree. If it's elongated, they disagree. And then finally, if we do have ground truth, we can highlight the border if it matches the ground truth. So as an example here, we see that in the first node on the left that the model 1 agrees with ground truth, and the next one, they both agree with the ground truth, and so on. And so the cool thing about this is if you see something like this, you can quickly figure out that, okay, model 1 predicted positive, the other one, model 2 predicted neutral. Model 1's more confident the distributions are vary significantly, and model 1's right. So that's cool. We're able to encode this information. But then if you look at the graph, you can look at whole kind of regions of the graph, and you're able to see, when you see these kind of two-tone regions, that this is an area where model 1 consistently said positive, model 2 consistently said negative, model 1 is correct more often, and then this is a way that users can then dive in and explore more. So I've talked about 3 different graph learning patterns and 3 different nuggets. We, of course, really want to combine all of this together. We have some first steps in doing this, but it's a challenging problem. And in closing, to address some of the questions that Ashish had mentioned, so I think in state of the art, we can use ideas from HCI about the unit of interaction, the context, and comparison, and use that to help us inform our design of machine learning algorithms. The challenge as we go to richer data, graph data, and so on is this becomes much more complex, and I think one of the opportunities is for coming up with abstractions that work both for the interaction for machine learning and for machine learning for interaction. So, thanks.
Do you have some comments, questions from audience? Yeah, Iche.
Thank you for the talk. My question is, in real world, many graphs are not static. They are changing all the time, and there are also patterns for the way they are shrinking or growing. What are your thoughts about learning about the temporal behaviors of these graphs? And are there any input we can get from humans in learning these patterns? Thank you.
Yeah, so definitely the fact that the graphs are changing over time is incredibly important, and figuring out whether you can develop a visualization where part of it is to allow the user to understand the changing over time. I have done some work where we've looked at changing interactions over time, and they're again trying to figure out what the way to visualize the stable part of this and how to see things evolve over time was the nugget that we found there. In terms of machine learning for being able to discover the patterns, like you were saying, the types of more global patterns in changing dynamics, I think there is a fair amount of interest in that. I'm not aware of work that connects that as much to the visualization of it, though.
Hi. One could also consider incorporating feedback from a user in terms of constraints, which could be runtime constraints, and perhaps some weighted combination of the learned model and these runtime constraints. So what are your thoughts about incorporating user feedback as constraints in graphical models?
And are you asking specifically about user constraints about computation time, so that it's...
Computation time is one thing. The other thing is, some of these constraints, you may want them to be hard constraints, and incorporating them as either features or in the form of labeled examples might not really give what the user desired. Perhaps while giving the feedback, it might just disappear in an ocean of other signals that the model has been receiving.
Yeah, so not so much in what I presented here, but very much a part of the kinds of joint probabilistic models that I'm interested in developing, having a way of encoding a rule, a probabilistic rule, and being able to say, give that an infinite weight, and the user can be the one that's giving that weight, if one likes, makes a lot of sense. And then being the interesting research as far as making that efficient, so that, say, you learn a model and then the user inspects that model, then the user adds in that constraint and figure out how you don't have to relearn that model again from scratch is possible and very interesting.
All right, let's thank Lisa again. Thank you, Lisa. All right, so next we have some representation from HCI. So I'm very pleased to welcome James Fogarty, who's been a long-time friend, collaborator working in this space. And he's going to talk about scaling interactions for machine learning. James.
Thanks. Is my mic on? Sounds like no. Yes? Oh, OK. Do you have the? Great. So Ashish asked me to talk about some of the state of the art in interaction with machine learning and where that's going over the next 10 years and some of the challenges to getting there. And so I figure by acknowledging that with the title slide up, I can now talk about whatever I want because I've covered everything I was asked to do. When I talk about the need for scaling interaction, where I'm coming from is that the looming big data boom breaks everything that we know about interaction, right? And so this is sort of the history of computing in 4 icons. In the beginning, there was the command line, and I hear there were things before that, but we're going to ignore that for now. But in the beginning, there was the command line, and that worked great for a couple things that you can keep in memory as you looked at them, right? And then we started to point at things, right? And then there were too many things to point at. And so we put them in bigger and bigger hierarchies, right? And then we couldn't find them in the hierarchies anymore. And so for 20 years, we've been getting by on search, right? So we try to guess keywords that will help us find the thing that we're looking for. And my point here is this no longer works, right? So if you look at web image search, it's already obvious that the keywords that are available do not match the distinctions that you want to make in images. And if you think about having a personal log of all the sensor data from your life, how do you keyword query into that? Right? The words are not expressive. They don't correspond to the distinctions you want. And I see machine learning as our only tool for scaling onto this challenge. Right? We have to have some way of articulating what we want as people from our data and from our information systems. And we have to be able to articulate that over raw data, and the system has to be able to generalize it, because otherwise we cannot scale to this volume of data. So given that, the current state of machine learning is designed for 2 categories of people, people who have PhDs in machine learning and everybody else, right? And so I'm going to approach this by breaking it down along that line. First, let's assume you have a PhD in machine learning or a closely related topic such as statistics or something like that, not just computer science. That's not close enough. There's a bunch of really, really great domain-specific tools out there, right? These are just 2 examples. There's a lot more out there. Crayons is a very well-known system. It's for training segmentation within an image classifier. You literally just color on the images in order to teach it a classifier that corresponds to the distinction you want to make in a bunch of images. And you pull up new images, color on them until it's doing the right thing, export it, put it in your application, right? On the right here is Exemplar. This is a system done by Bjorn Hartman and colleagues. This is for training sensor-based interactions. You demonstrate what you want to recognize with some simple sensors. You can see the visualization of the sensor data. You impose some filters over that, do some highlighting of what it is you're interested in recognizing. It does some dynamic time warping algorithms and matches that. These are great. If you have a PhD and a system like this exists for the problem you want to solve, you're in good shape. It hides a lot of the complexities, and it exposes just the right interaction that you need and provides an entire pipeline to implement that problem. OK. You still need the PhD to find out that it exists. You got to know all the right keywords to query. You got to be able to assess it to determine whether or not it actually solves your problem, right? If you're trying to do object recognition with crayons, you're going to have a bad time because that's not what it's for, right? And so you still need that PhD. Now, on the other hand, if you can't find that system or it doesn't exist, you're back to using general purpose programming tools, right? And so I've just got some examples up here, but you might implement some feature extraction in a system like Python. You might, if you're a Java person, go to Weka for your library of learning algorithms. And if somebody's paid for you to have a site license for Tableau, or you've got some other in on that, you might get some great visualizations of the different experiments that you're running and how that's working. And now, the problem here is that this is a patchwork process, right? And so in between each of these, you probably have some scripts that change your data into the different formats it needs to be. And when you get to the end, you might have something really simple like a confusion matrix, right? And you want to say, OK, I want to click in my confusion matrix and see the example that was misclassified. And you can't do that, right? Because your raw data is long gone, right? That was the input to the Python scripts. That's not in the learning environment by the time you actually get there, right? And so there's this patchwork. You can't iterate across it. You can't deploy it at runtime. And so you're just stuck working among these tools. One of my former students once described this as giving up all the niceties of, like, if you do modern web development, your IDE understands deployment to a server. It understands different file types. It understands version control. But K.R. Patel said that when you go do machine learning, it's back to floppy disks and flat files and things like that around your machine, right? There's just no understanding of the structure. And so some of the work that we've done is looking at what does it mean to build an IDE that supports the process of applying machine learning, right? We're not going to support any particular machine learning problem, but what we're going to do is support that process, understanding that we're going to start with raw data. We're going to extract features from it. We're going to apply transformations onto those features. We're going to train models. We're going to wrap all of that inside an experimental process as we try to determine whether our system is effective or not. And so this is where I think there's a huge opportunity for better tools that are not particular to any one specific domain, but particular to the process of something like supervised classification, right? And so in Gestalt, the way that we did that was supporting scripting, having this pipeline explicitly represented in your IDE, supporting scripting of the different stages of that pipeline, linking that through a shared data table, right? So the rows and columns that Lisa mentioned, but linking that through a shared data table to visualizations, because you don't debug machine learning with breakpoints, right? You can have all of the breakpoints in your program, all your code is right, but the thing still doesn't work, right? Because your data is not good enough, or you have the wrong algorithm. And so linking all of that inside of one tool within which people can quickly implement different kinds of classification algorithms. So that's trying to make it easier to do machine learning if you almost have a PhD in machine learning, right? So trying to bring that closer to your everyday software developers who maybe took one graduate course in machine learning, right? But let's talk about everybody else. So let's talk about the people who use the systems that we actually put out into the world, right? And so the state of the art there is really drawing upon 4 different high-level strategies, right? And there's a lot of things underneath these strategies and some really clever designs and some really nice research. But basically, a lot of it comes down to explicit prompts that can guide learning, right? So this is active learning. This is other things. But we're going to explicitly prompt a person for some feedback in order to guide the learning process. We might, if we have lots of people available, aggregate the feedback we get from all of these people so that we have to ask any one person fewer questions, right? On the other hand, we might not want to ask them. Maybe we just passively observe, right? So we watch them using something. We infer from that and try to give them what they want next time. And lastly, if we have lots of people whom we can passively observe, we try to infer some higher level thing about the world and come away from things smarter and more helpful. Right? Now, if I can be crude for a moment, because Ashish encouraged me to create controversy and discussion also, I claim that none of these things empower people. And so explicit prompts are often conducted using flat files in an experimental context, right? So your person is just an oracle. And when we're a machine learning person running an experiment, we simulate that person with a file, right? And so it's not really designed to encourage or enable the person, right? And if we aggregate that across lots and lots of people, then we're just treating the person as sort of a faceless member of a crowd. Yeah, I know you said you wanted to watch this video, but everybody else really likes Justin Bieber, and so I'm going to show you Justin Bieber, right? Your individual opinion gets dominated by everybody else's. The passive observation, so if you have a dog, you really want to help the dog, right? But the dog can't tell you what it wants, and so we just try to watch it and guess what it needs and try to give that to him, and because we can't ask the dog, right? And if we're watching a lot of rats run around in a maze as part of some bigger experiment, we might be learning a lot, right? But we're not helping the rats, right? And the cheese isn't really helping them based on what we observed. It's just cheese, right? And so what's missing from all of this is really empowering everyday people to use machine learning to their own ends, right? There's this perspective that we as a software developer know what the machine learning system should do here, and the user is just going to provide guidance. But what we want to do is empower people to use these systems to their own ends. And so we've done a little bit of that with my former student. I guess you're still my student. It's lifetime, right? Salima Mershi over here. These are two different systems she did in her dissertation work. She now reports to Patrice, and so we were discussing what that makes Patrice and I. It's like weird cousins or something. But so QFlick is in the context of web image search, right? And so if you're doing an image search and you're finding that the keywords don't allow you to make the distinctions within the web that you want to make, you quickly interactively train up a classifier and then can use that as a filter in combination with the keywords that the search engine is already providing. So a person is in the middle of a task. They decide that they need to create a machine learning system to assist them in the task. They do that, and then they return to that search task. Similarly, on the right here, we did regroup. This is for social networks, for training groups of friends with whom to share content. And so looking at how a machine learning system can help you in the individual task of sharing some content with your friends. And this is some more recent work that I've done, looking at empowering end users to control their own sensor data. Right? And so if you're familiar with Fitbits, this is a detailed step log of somebody, all of the steps they got within some day. And in this scenario, the person is extremely happy because they hit a very big step goal for the day. And they want to share it on Facebook, this detailed data. The problem is they got most of their steps walking home from the bar at 2 a.m. the night before. And so they don't really want to share that with their parents. So what's going to happen here is they are going to interactively highlight that data, tell it to go away. It's going to be reassigned within the same day. And so in this case, it looks to their parents like they walked home from dinner, right? And so what we're doing here is a bunch of motif discovery, trying to find realistic patterns in your own historical data to empower an end user to interact with something as low level and complicated as raw sensor data, right? And do that in a realistic way. So when I started out saying that this is sort of the state of the field, where we need to be going is towards really understanding the diversity of skill sets, the diversity of problems that exist between a naive end user who cannot and does not want to interact with machine learning up to people with PhDs in machine learning. Right? There's software developers along the way that had one course. There's sort of people who have an analyst perspective, or there's somebody who's willing to train something as long as you can make it easy enough for them to do. Right? And we really have to understand that different designs are going to work at different points in this space. There's going to be some general ideas that we can distill across them, but there really is a spectrum here. Most of that spectrum currently goes unexplored. Right? And so part of that is because the bulk of the machine learning community is interested in making that person with a PhD more powerful. Right? We're working towards a superintelligence, and so we're going to keep pushing the end of the spectrum further and further that way. It's a generalization, but I'm supposed to be controversial. So, and in the HCI community, I can criticize my own community more strongly. In the HCI community, if you take something that's possible for a software developer and move it over into the middle here, the critique you'll often get is, well, but an end user still can't do it, so you haven't made any progress. Right? There's this desire in the HCI community to distill everything down to the lowest common denominator, where this entire spectrum is actually really compelling. And personally, I find this really compelling because I think this is important for computing to remain empowering. Right? If we're going to create this big data revolution, we're going to have all of these powerful analyst tools, all this incredible ability to distill things. But you can only do it if you can assemble a team of 25 PhDs in machine learning. Then who's going to have access to that? Right? And we really need all of us to be able to do that. OK. So that's my slides.
Right. Thank you, James. Any comments, rebuttals?
It's very interesting to see you actually want to do the
more into the everyone can do the machine learning. And that still, what if you do the big data or whatever application, you still have lots of the application domain knowledge. How do you envision that could be, be conquered by the barrier, but for everyone? I still didn't see the clear roadmap can clear that barrier.
Yeah, so there are parts of this that are going to inherently be the domain of like the expertise of signal processing people. So, for example, John Freilich is here in the audience, did some great PhD work on a system called HydroSense. The idea here is that every time you turn on or off a water fixture in your home, there's a pressure impulse that gets generated, right? And you can train up lots of really sophisticated signal processing systems to recover what fixture was generating that activity, right? And I don't think you're going to get grandmom to build that system, right? What I think we can do is realize that we as the developer, if we build a water conservation application based on top of that, that's going to give people individualized feedback about how they're using their water and help them make better decisions around that, you need to give me the ability to make the distinctions in the data that are important to me. So I recently resumed running in hopes of eventually getting back to being able to run a marathon without dying. And if I want to set a goal that says the shower that I take after I go for a run will only be 2 minutes long, right? Whereas the shower that I take in the morning might be longer because I also shave, then that is a distinction that I need to be able to make in the data. You have all of the signal. You have the water usage. You have my Fitbit data. You know when that happened. But right now, you don't. We as developers don't give end users any way to express that desire over their data.
Any other questions, Andrea? You can take this mic.
So related to that, how do you think? So it seems like in a lot of the examples, the feature space is pretty well defined. So how are we going to get to having where the programmer or the designer has to be talking in feature space, not in the algorithm or the end goal? Because I want the user to be able to define their own features, their own goals over this feature space as opposed to this particular goal.
If I had a brilliant idea there, I wouldn't say it out loud. I would go write a bunch of papers and grants about it instead. I think we've seen some great work around interaction with text, right, where it's really easy to visualize the feature if your model of analysis is a bag of words and other things like that. I think there's a big open opportunity to take some of the ideas that have been explored there and think really hard about how to extend them onto other kinds of data and other kinds of representations, right? And I think it's a huge open problem.
Yeah, to add to that, it's just not text. Like 99% of interactive machine learning stuff I have seen is also dealing with visual tasks, computer vision. So it seems like while you are interested in end users, it seems it's end users who are interested in text and vision only.
Yeah, well, pixels and text are both easy to visualize.
Yeah.
Right, and there's a big visualization question and a big composition of visualization questions that comes up with other kinds of data. And so Lisa's graph visualization there is making something more subtle and complicated visualized. And I think it's really interesting to think about good ways of doing that for a wide variety of data across these different domains.
Great. Thank you, James. We'll move on to Patrice. Let's see. All right, so you're on here.
Is there a clicker?
Yeah. So let me introduce Patrice Simard, who's a distinguished scientist at Microsoft Research, and he's been spearheading some efforts on interactive machine learning to tackle web scale data. So with that, Patrice.
Thank you.
I think it's not going to work with that. You'll have to tap it here.
Tap here?
Yeah.
All right. Okay. So I'm going to reach the same conclusion as James from a completely different point of view, given that I'm a machine learning expert by training, and I will. When I started, I was thinking. Well, actually, let me go back a slide. I was motivated by solving a real problem, an engineering problem, and I thought I had a big hammer. I'm a machine learning expert, so probably I can solve it with machine learning. And I came to the painful realization that the problem was the machine learning expert, and I had to basically think about other ways to solve the problem. So, and this is where my conclusions are very similar to James. So let's solve by the problem. So the problem is that, actually, maybe, I can read here. Okay, the problem is that there's a lot of value that's locked in the data. And it's locked in the data because the data is typically unstructured. We have queries, we have web pages, we have people writing ads for their product in eBays and their tweets, and there's lots and lots of data, and it's unstructured, and that's the problem, because if we want to match a query with a web page and we don't understand neither the query or the web page, it's going to be hard to make a system that's very relevant. And so, so there's a lot of value if we were to be able to understand this unstructured data. Problem is that we can't easily extract it. Now, humans are very good at extracting that kind of value because they can look at a web page and tell you very quickly what it is. The problem is that they suck at scale. I'm sorry to say it this way. The machines excel at scale, and they kind of suck at semantic understanding. So we have a problem, and the truth is we can actually solve that problem in small, very constrained environment. And so we can build classifiers that are actually pretty good using machine learning. The problem is that we can't do this at scale. And so when we do this in Bing or in Google, and the way it typically works is that some program manager decides that we're going to build a classifier for a particular task. And we go and collect some data. And the data is biased because how do we find positive? If I want to build a recipe classifier, I need to find a few recipes. So I'm going to search for recipes. I'm going to get a bunch of recipes. Then I'm going to send them to India or China to get labeled. And then I'm going to do some feature engineering. This is where, being a machine learning expert, you get highly paid to solve that problem. Then we deploy it, and it's a catastrophe. And it's a catastrophe because we built the classifier thinking, we collect a bunch of data with, to do, let's say, recipe classifiers. And then we deploy it, and it finds that numerical recipes is a good cooking recipe, and cement mixing is a good cooking recipe. And then we miss the Ethiopian or African recipes because we had no idea about this when we solved the problem. And then, of course, the consumers tell you that your system sucks. And then you go back and you do another iteration of this. And every iteration is very, very expensive. We're talking about weeks or months. And this is not, and this is just for one classifier. Imagine you wanted to build 100,000, and now you have a problem because machine learning experts are well paid and they are rare, and hiring them is a problem. And also you need an infrastructure to do it. A small company cannot do this easily. And so really the problem is that we have to cut the machine learning expert out of the loop, because otherwise we'll never be able to do something at scale. So so let me just illustrate what the problem is in a very, very small, simple way. So we have a set of positive examples that I can collect by doing queries, and I can find a few negative examples, and I can build a classifier using these examples, and if I'm lucky, my thing will generalize and find all these positive examples. It will not get any of the negative example I put there. Then I deploy it, and the problem is you can see where the cooking, the numerical recipes and the cement mixings are in the negative example. I wish I had known when I collected my data. And same, there's a lot of data that I missed. And so the problem is that I want to build a system, but it's not going to be robust against what I don't know. And that's the problem, because if I want to deploy something useful, it has to have those properties. So what can we do? Well, the solution is interactive machine learning. So it's a good place to be. So we have to change the loop completely to solve this problem. And the idea is, and there was some question about which kind of problem we can do, and I'm going to make a lot of restriction. I'm going to restrict the space to a problem on which I can collect n item of the same type, whatever the type. It could be query, website, or whatever. And then on these, I'm going to work on building classifiers, lots of classifiers, lots of entity extractor, form fillers. And that's a huge restriction. I'm not going to do graph understanding, which is much harder. So I'm restricting the problem to be really simple so that at least I have a chance, engineering-wise, of coming up with a solution. So I collect this large amount of data, but when I collect it, I don't know what classifier I'm going to build. So the nice thing is that I can reuse that collection step. Then for each classifier and entity extractor, I'm gonna sample the data, but I'm going to sample it with a classifier in the loop. So the nice thing about having a classifier in the loop is that it can score. It can score very fast, 100 million example. And once it's scored, then I can pick the examples that give me somehow the most information. Now, I don't want to maximize the amount of information, because if I do that, then I get all the ambiguous cases, and now my labelers is just going nuts because it's all ambiguous and all really hard. So I have to find a way to extract good information without being too painful. And if I build my system right, as soon as I have a few more examples or a few more features, and there was a question about generating features, I'll talk a little bit about that, then I can retrain my system, and that, because I've just inputted a few labels, typically the number of labels is not very big, so I can retrain this very fast. And now I can rescore my 100 million. And if I build my system really well, then I can do that in this almost a sub-second time frame. And now my whole iteration is a couple seconds. Between the time I label, I enter a feature, I retrain, I rescore. And now the problem is changing. And putting that dynamic changes a lot of things. Like, for instance, I'm starting to build my recipe classifiers. And I discover cocktails. Are cocktails recipes? Well, I can make that decision on the fly. I don't have to go back to my program managers and say, well, you know, blah, 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 or we're going to rewrite the labeling directives and we send it back to China. And that, you know, the nice thing is that if it's interactive, then you're going to learn as you go what the data is, how you should adapt. And that will change probably how you build your classifier. So, so the idea here is that we're going to take the machine learning expert out of the loop. So my job is to put myself out of a job. And I hope I succeeded. Well, yes. So the nice thing also is that now that we have this instant feedback loop, then what happens is that you get good at labeling and at featuring. And now it's very different. I believe that someone using our system I will trust more than someone with a PhD, because they've had that interactive rubber meets the road contact with the data. And that's not always the case for all the machine learning experts. So this is a good thing to be able to do. So also we'll be able to share the infrastructure. So when we build classifiers, then I build features, and the features, just to answer that question, the feature we do interactively right now, because we're doing a lot of textual data, web pages, we want the user to input what I call concepts. And so with bag of words, you have a bunch of words and they're not related. But if you build an automotive classifier, you could put a list of car brand. Now you have one feature, which is the list of car brand, and now I measure in each document how many car brand are in that document. That's what I call coverage. And the term frequency, how many example of car brand there are in that document. And so I have actually two features for one dictionary. But then I run the system and I have maybe a radio control car coming up. And if I ask the labeler, why is that a false positive? And they know, they've labeled it. So they immediately have the answers. Well, it's a radio control car. And well, how do you know? And they say, well, it has channels, megahertz, antenna. And now we can build another dictionary, which is a concept again. And with that feature, the classifier can now disambiguate between the two, which it was colorblind just before. And now with this interaction, and then you can imagine how this repeats. You run the system again, and now you find toys, like the toy Porsche, and Lego or Fisher-Price. And now you can put a dictionary of toy brand. And with that concept, now suddenly the classifier is no longer colorblind and can get those again. And of course, if you put too many features, at some point, you need more labels, because putting a lot of features without labels won't get you anywhere. So you have this basically iteration between label and featuring. The nice thing about having a system that have that kind of architecture is that there's no surprise. The data you've collected, so my first really anxiety when I started working on this problem is, how do I get an insurance against what I don't know? And by what I don't know is that then I'm going to deploy the system and it's not going to work, because it's going to discover things I've never discovered before. But remember, the data collection stage basically picked 100 million examples. And with 100 million, I can actually summarize the true distribution. And so when we have this interactive system, we are constantly interacting with the true distribution. It's not a sample distribution. It's really the true distribution. Now, there's lots of challenge with this, but the nice thing is that if I do this well, and we haven't solved all the problem there, and this is why we're still talking about it, the problem is not solved, we should be able to build a system that when we deploy it, there's no surprises. Now, right now, I guarantee you that we would have a lot of surprises, but basically this is where we aim to going. And I think with this approach, we have much more of a hope of success than with the previous approach. So here, basically, this is a shameless plug for demo tomorrow at 10 o'clock, from 10 to 1, where basically we have built such a system, and you would be able to build a classifier with no machine learning expertise required. I think we can build a reasonably, not the state of the art, but pretty close, well, a reasonably good classifier in let's say 5 to 15 minutes. So this is what the demo is about tomorrow, and we have an interesting infrastructure in the back where it's 60 machines. Each of them has 128 gig of RAM. So we could theoretically have 500 million web pages in memory. And we could reclassify all of them in a few seconds. So this is a nice thing. Now, there's lots of problems. There's UX. We have a mix of machine learning expert and engineers and UX expert, and this is the composition of our team. And I think we need all of these skills to build that kind of system. The curve on the right is basically trying to show the histogram of the distribution. If you have a classifier where it's mostly negative, then after training, you have a curve that looks a little bit like this, where if you were to sample close to 0, that's the probability of your system basically saying that the probability of finding a recipe in that region is almost 0. You don't want to sample there, you don't learn anything. If you sample close to 1, you may not learn as much. If you sample in the middle, it's actually pretty hard because it's ambiguous. But if you sample at 0.25 and at 0.75 and your system is calibrated, then 1 in 4 you find a surprise. And now when the user basically gives you that label, that gives a lot of information for the system to get better. So on this, I'll just summarize the challenges, and it's one of these things. You have to have 3. If you have less, you're not serious, and if you have more, nobody gets it. One problem is sampling lopsided data, and all the IID assumption cannot work, because if you sample IID, then it will take you 1 million label before you find your first positive, and if you put a bias, then you have all sort of problem. Then the second problem is measuring progress, because typically you measure recall and precision, but how can I measure recall? I don't know how many positives there are. So I need to find other ways to measure recall, and we have something that sort of works. It's so noisy that it doesn't quite work, but this is an area of research. Then there's featuring and debugging, and now the problem is how do I engineer my features to get good recognition? And and remember, I built this system so that my mom can build classifiers, and if the features are very complex, she's not going to have any interest in doing this. So it has to be really simple. But now, if it's really simple, and I'm trying to tell Bing to build a system like this, then they're going to say, well, and how about the accuracy, right? And this is where we try to find a way to regularize the information provided by the user in a way that will get you the accuracy of a system built by a machine learning expert. And the third one is infrastructure, and there's all sort of interesting thing, challenge. And all of these are mixed between UX and machine learning. Like for instance, if I build a system where people share entity extractors and classifiers, this is one thing I like about democratizing. If we democratize something, we're going to get a whole lot of crap. But the nice thing about having a lot of crap is that you can pick the gems, and then we can put all sort of system to basically evaluate the good classifiers from the bad classifiers. And if we have that problem, this is a great problem to have. And this is a problem I hope that we're going to have. We're going to have a lot of crap, and then we'll have good things to choose from. All right, it's probably time to stop.
Great.
All right, thank you.
Thank you, Patrice. Any audience questions, comments? Yeah, there's one over there.
So thanks for the nice talk. You mentioned part of the problem being positively labeled data and negatively labeled data. Majority of the novice machine learners are now struggling increasingly with lack of negatively labeled data. So we only know a lot of positive instances, but there is a tremendous plethora of,
assume everything is negative.
Yeah, assume
Problem
everything
solved.
is negative, and so any thoughts on that?
Yes. So imagine you assume everything is negative, but your system is interactive, so you have a classifier in the loop. So everything is negative. Well, there may be some errors. Because you've labeled a few positive, now your classifier is not completely stupid. And you could show all the negative sorted by the confidence that the classifier has. And now if you have put a few positive, these will absolutely pop out. They will be the classifier where the example in which the classifier is the most confused. And if you show that to the user, they can immediately correct them. So that's this actually is not a big problem. It's not the one that keeps me awake at night. Just assume everything is negative and just verify. And that's in some way, a lot of people assume that, and we've built lots of things like this, and even with machine learning expert, I have this fight all the time. A lot of people assume that the quality of your data depends on how much data you have and what is the quality of the label. And neither of these is important at all. The only thing that counts is how much is your system going to generalize? And so the analogy I like to make is that if I want to measure temperature in the United States, I can buy $1,100 thermometers and put them all over my basement. And that's not going to do very well. And even though they are super accurate and I have lots of them, if I put 50 $1 thermometer, one in each state, it's going to be way, way, way better. Right? So so I don't care about labeling accuracy, and I don't care about labeling quantity. I just want a few labels. And so what I want is to build a system where you can label very quickly and make a lot of mistakes. Because your classifier is in the loop, you can verify these things where the classifier says, hey, you know what? It's not very consistent here. And now I was falling asleep and I just started labeling, and there's a little bit of information, but not that much information because I'm not that awake. But then when my system basically verify and there's ambiguity, then I can go back and revisit exactly those that were maybe not consistent. And so I don't have to worry about quality of label. I don't even have to worry about bias because I can basically assume everything is negative and then revise it. Maybe longer an answer that you wanted.
That's fine. All right.
So how do you handle evolving label space? So your label space might evolve?
It's binary. Yes. And we can have, there are lots of advantages in being binary, and that's, again, we want to maximize efficiency. I don't want, and I've built a lot of labeling tools as an engineer, and they all suck. And this is why we had to basically, and every engineer, they think, oh no, I don't need a good UI. But the thing is, one of the labeling tool we were trying to label addresses, and on every word you can right-click and bring a menu of like 6 different things. And labeling an address would take 30 seconds to a minute. And instead of labeling vertically, which is what we call this, we could look at a lot of address and find just the city and verify that the city is there. And again, since I don't care about quality of label, I can show probably like 50 addresses on the page. And if something is suspicious, you'll see maybe there are 2 cities, or the cities is at the beginning of the thing. Then you immediately zoom on that and you verify that. And now I can get 1 or 2 seconds per address, right? But everything is binary, and every time I click, it just flips that thing, and that's basically it's optimized for speed and efficiency. Yeah. Because my mom doesn't have that long an attention span. So.
All right. So last remaining three minutes. What I would do is I would just ask each of our panelists to, maybe say a couple of sentences on, what they, like if they, if they learned anything, or if they anything that's, they disagree with. We can start with Jerry first, and just stand at your place and just, say things. Okay, I think that's easy.
Okay, so I think this is great that the discussion really brings up in my view, an opportunity to, from my perspective, to actually quantify a lot of the empirical work and put them on maybe on a theoretical foundation. That's, I hope, how we can continue this discussion.
James, you have the next?
Sure. Yeah, so I just thought this was really great to see the different perspectives, and I think I'll push back on anything on Ashish's distinction between the session on, well, how do we train learners, and then the session on how do we benefit from learners, because I think it's a give and take, right? I mean, we're doing it in both directions in a lot of contexts, sort of like learning versus teaching, right? It's a thing that happens together often, and I think there's a bunch of interesting opportunities there.
Lisa.
So I thought one thing that was interesting and consistent across all of the discussion is the need for better exploration of features and feature acquisition. And in my mind, that actually is the secret sauce of going from graph data to the flat data, is the kind of hammer that you use to flatten it, and then exactly how you put together those flattened pieces, whether you treat them as kind of independent classifiers, or that maybe you want to, have this method for building your node classifier and have this method for building your link classifier, and then have them interact, because that link classifier could actually be the feature that then is going into your supervised problem. So, yeah.
Thank you. So, last words, Chris?
Oh, well, I can use this microphone.
Mic, yeah.
So I'm very happy to see that I prepared my talk without looking at the other speaker's talk, and I was very pleased to see that we all conclude in the same way. And the thing that's interesting is that machine learning is a big part of this. And when you think about it, if you do interactive machine learning, you cannot have the ID assumption. And that's a big problem, because ID is what allows you to write a paper. Because in machine learning, you assume that the training and test distribution are the same, and that assumption comes from the data being ID. If it's not ID, you can't write a paper, and that really is a shame, right? If you're in that field. So the fact that basically we have here like 4 academics very committed to this field, and we know this is going to be a hard battle. We know it's going to be hard to be successful, because right now we don't have much of a deep theoretical foundation to publish results. So I'm very excited about the fact that we're committed to solving this problem, and that makes me very happy. And so,
great. Yeah, thank you, everyone. Just want to remind you that there is a sister session coming up at 2:45, and let's thank speaker again. And I hope to see you at 2:45.